Hey guys, thank you all for coming today to attend this review online. And I hope that y'all are doing well, especially as it is finals week and I know it's stressful. And I hope that your exam prep has been going well. In this video, we'll be covering a previous year's final, the 2015 final, along with a few practice questions, multiple choice questions, from the ACS Organic Chemistry Review. So let's dive right in. For question A, these are a set of nomenclature questions, as is the case for the exams, the first question. And we're asked to give the IUPAC name for the compound. So let's take a look at the functional groups in this molecule. So we see immediately right away that we can notice some hydroxyl groups. And when you see hydroxyl groups and you don't see other substituents such as carboxylic acid or higher priority groups, you can right away tell that these are going to be the priority groups to consider when we're trying to evaluate the nomenclature of this compound in particular. So the question becomes, well, how are we going to determine our parent? So the case is when you have multiple hydroxyl groups on a compound such as this, you have to find the chain that has the most number of carbons, the chain with the most number of carbons and a hydroxyl group in that chain. And you have to compare the options that you have, and the one that has the most carbons is the parent chain, while the other one becomes the substituent chain. And that's what we'll see when we go about and try to solve this problem. So when we try to find out what the parent is, we see right away that there are two options present. So the first option is this cyclopentene ring. I mentioned pentene because there is a alkene group right here, right? So we're not dealing with just a cycloalkane. So what this means is that we have to number our carbons, and we see that there are 5 carbons, right? It's a cyclopentene chain. And what's our other option? Our other option is this chain right here. Or alternatively, here. It doesn't matter because those are two groups that are equivalent. So you have two choices, right? You see that there is one chain that had, both chains have a hydroxyl group within them. And the difference, though, is that the chain on the right, the cyclohexene ring, it has more carbons, right? It has one more carbon. So that would make it the parent chain of this compound, so to speak. So what that means then is that we have to look at the function. We have to actually consider how the numbering of this compound would actually, of this parent chain would actually be. I had written down 1 to 5 just to get a count of the number of carbons, but that wasn't accurate. Now we want to consider the functional groups when we're actually numbering this chain out. So since the hydroxyl group is our main priority, it's the highest priority functional group, we would list this as the first carbon, right? And since we have a alkene group and we have this long branched substituent, we are trying to reduce the numbering. We don't want to choose a certain path that will give us a higher numbering for these substituents. So the best route to go is to go in this direction, because we see that the alkene, the first carbon of that double bond is at position 3. If we had gone the other way around, we would have to, the first carbon would still be position 3, but this long branched substituent you see here would have a position of 4. And in this case, the numbering gets more spread out, which is not what we want. So what we should do, actually, is just stick to this numbering and go ahead and list out our parent chain along with the substituents. So we've laid the groundwork. So when we look at this, we see that when we're including a cyclopentene ring, the numbering for denoting that alkene functional group starts at the first carbon. So what I mean is, if we're talking about a cyclopentene ring, we would have to include the number for that first carbon. So it would be 3 cyclo, but there's one thing that we didn't include, which is the fact that this also contains an alcohol, right? A hydroxyl group. So you would not put cyclopentene, you put cyclopentanol. So the all suffix is used to denote the presence of the hydroxyl group. So we've listed out our parent. Now the next step is to find the substituents. And in this case, that substituent is the branched hydroxyl group we see there. So in order to name this, we see that, first of all, it's a complex substituent. So let's number this substituent and try to see where the substituents within that substituent are located. So 1, 2, 3, 4. So now that we've numbered it like that, if we look at this complex substituent, we see right away that there is a methyl group at position 3 and a hydroxyl group at position 3. And in addition, this entire branched substituent, this complex substituent, is on the third position with respect to the main chain as well. So when we write it out, what we get is actually 3 and then parentheses to denote the complex substituent. So we're going to put all the contents of the complex substituent within the parentheses. We get 3 dash parentheses 3 hydroxyl, and we put the hydroxyl group first because of alphabetical order. 3 methyl, because it's following after the hydroxyl in alphabetical order, and then the parent, which in this case would be a butyl group. Now, you might think that we're finished, but there's one more thing to include, which is the stereochemistry. So when we look at this compound, we see that there's only one possible place that can actually have a stereocenter in this compound. And that place is this carbon right here. So in order to evaluate the configuration, let's apply the Kohn-Ingold Prelog, or the CIP, rules of convention. So right away we can say that the hydroxyl group has the highest priority, and then following that we would include this this part of the chain, and following that it would include the bottom part of this chain right here. So what this tells us, and since the lowest priority group is projecting inward into the page, if we draw an arrow from 1 to 3, we see that the stereochemistry is just the configuration for that chiral carbon is just in the S configuration. So now we have all the pieces we need to put the name together, and we end up getting the following. I'm running out of space, but let me just... For question 2, we are given a compound where it's a hydrocarbon with several double bonds in it. And right away, when we are trying to find the parent chain, what we want to do is we want to find the chain that has the most number of double bonds. We want to maximize the number of double bonds within the parent chain. And we find that we can use either this chain as the parent chain, or we can just use this chain. It doesn't matter because either way it's equivalent. So I'm just going to stick to the second option. We see that this this chain would be numbered from right to left, because if we numbered it in the other direction, we would actually end up listing the locations of those two double bonds at higher numbers, and that would be 3 and 8. In this case, they would be listed as 1 and 6, the locations of the double bonds, because we're starting off with the first carbon atom that we encounter when we run into each of these double bonds. So the name for this parent chain would be 1,6-nonadiene, or nana 1,6-diene. Now that we've figured out the parent, let's look at the substituents. So we see that there is a complex substituent at 4 and a methyl group at 7. So to list that out, that would be 4, 2, there's 3 carbons on the complex substituent, so that would be a propenyl, because there is also there's a double bond at carbon number, carbon number 2, so that would be the 2,2-propenyl. That would be our first substituent. The next substituent is the methyl at carbon number 7. And now the last part of this nomenclature that we have to find out is the stereochem. So what we find is that this case there would be cis-trans isomerism. And when we look at this, what we find is when we look at the main chain, there is no cis-trans isomerism for the first double bond, because there's 2 hydrogen atoms attached to one side, so that would immediately exclude that possibility. But if we looked at the second double bond, which is positioned between carbon 6 and 7, what we find is that the higher priority groups, so let me, just to be thorough, I'll add in the hydrogen atom here, and what we find is that if we were to tilt this molecule, this double bond would be horizontal, it would be easy to see that the higher priority groups, which are in this case this whole substituent and this whole substituent, they would be on the same side of the double bond, right? So these two groups have the same priority. They would be on the same side. So by the rules of EZ notation. So I apologize, not cis trans. What I meant is you can use EZ notation here, and what you end up getting is a Z since they're on the same side. And so when you write out the final answer, and one more thing, there would be, since this is referring to the carbon at position number 6, that's how we would refer to this double bond, so starting with the first carbon that we run into by, according to the numbering of the parent chain, that would be at carbon number 6. So we can write it out as 6Z. So 6Z. Now when we look at the substituents, we see that the methyl group has would be placed first because of alphabetical order. 7-methyl, 4,2-propenyl, and then for the parent chain, I'm just going to choose I'll go for 1,6-nonadiene, but either way, it's your preference. For question 3, we are given a compound that contains a cyclohexane ring along with 2 substituents. So let's go ahead and try to identify the parent chain. We see right away that if we number these substituents, none of them have 6 or more carbons, and this tells us, in fact, that the cyclohexane ring is indeed the parent chain. So, quite simply, cyclohexane. Now that we've listed out the parent, if we look at the substituents themselves, let's start off with the one at the top. We see that the substituent has some branching, and if we look at the numbering, we see that there is a methyl group at carbon number 4 of that substituent. So when we write out the name, what we end up getting is, and we haven't written out the numbering of the parent chain yet, but we'll get to that. So we write it out as 4-methyl, and since there's 5 carbons comprising of the main chain, we can write it as 4-methyl pentyl. Now the second sub would be this simple butyl group right here. Now again, we can go in 2 directions when we're numbering the parent chain, right? We can go 1, 2, or 1, 2. It won't affect the numbering either way we go, but we have to take into consideration in this scenario the alphabetical order of the substituents. And so we see that the butyl group would actually be given the position of the first carbon, and the branched substituent would be given the position of 2, because we're looking at the alphabetical order and B comes before M. So when we write it out, when we add the numbering for the positions, what we get is that. Now, the last thing we need to consider in this scenario is the cis-trans isomerism. And so when we look at this for cycloalkanes, when we look at cis-trans isomerism, we're not looking across the double bond, right? We're looking at whether they're on the same side of the ring. So that means that one would have to be axial up and the other one would have to be equatorial up, based on how we would place the substituents in a cyclohexane ring. So that's precisely the case in this scenario if we want them to be cis. So we see that the complex substituent is axial up, and this butyl group is equatorial up. So that would mean that we have to write it out, the stereochemistry, as cis. So when we write out the final name, it would be cis 1-butyl 2,4 methylpentyl cyclohexane. For question 4, we see a Fischer projection of a compound. And this actually helps us in our task of finding the IUPAC name, because for two reasons. The first being that according to the rules of Fischer projections, the longest chain runs down the middle, and that includes the groups at the top and the bottom. So these two groups, we would include those carbons in the main chain along with the carbon at the center of the projection. That would comprise our main chain. So that's the first reason. And the second reason is that this Fischer projection right away tells us that we need to consider chirality, because that central carbon, since it has 4 groups, right, 4 different groups, there's no 2 similar groups. We know right away that that is a chiral carbon. So it already tells us to pay attention to stereochemistry. So with those two things in mind, we can go ahead and start the process of finding the name for this compound. So the first thing is, again, finding the parent chain. And we had already discussed the chain down the middle, the line down the middle, including the groups at the top and the bottom, would comprise the main chain. But now the question is, what's the right way to number these carbons so we can reduce the numbering, and which is what we're looking for in the parent chain when we're trying to find the name for the parent chain. And we notice that there is a triple bond between these 2 carbons, and we know that when we have bonds that are not sigma bonds, so in this case a triple bond, we are trying to make sure the numbering is in such a way that the number corresponding to that would refer to the triple bond, the position of the triple bond, is as low as possible. So that would actually mean that we would have to number in this direction, since the carbon would be at position 2 as compared to, say, position 7. So this helps us in our trying to determine the name. So we see that there are 8 carbons, and that means that along taking the triple bond into consideration, we would list that name out as 2-octine with the -eins suffix at the end to denote the triple bond. Now let's look for the substituents, and in this case it's rather simple. There's 2 bromo groups in this chain, one at carbon 5 and one at carbon 8. So this would simply be 5,8 dibromo. Now we have to determine the stereochemistry of this chiral carbon. So in order to do that, let's list out our our groups by the CIP rules. And when we do that, we see that the bromo group, being the group that has right away the highest atomic number, we would list it as the highest priority group. And now we are, obviously the hydrogen would be our lowest priority group. And the next two would be, we have to look at the first carbons. They are attached to two hydrogens, so this doesn't tell us anything. But if we go one carbon down further, we see that this carbon is not attached to any hydrogens. It's just attached, triply bonded to an adjacent carbon atom. So what this tells us is if we look at the other carbon, it's attached to two hydrogen atoms along with a carbon atom, and this is lower priority than having a carbon just being triply bonded to another carbon. So by CIP rules, we would just list this as the second highest priority and this group as the group with the third highest priority. So if we were to draw an arrow from 1 to 3 in this fashion, we see that the configuration, that the apparent configuration would be R, but we have to take into consideration that this proton right here is by the design of a Fischer projection coming out of the page. And when your lowest priority group is coming out of the page, we flip the configuration of that chiral carbon, the apparent configuration of that chiral carbon, to get the actual configuration. In this case, it would be S. And so when we write it out, now that we have all the pieces, we start again with the stereochem. And since this chiral carbon is at position 5, it would be 5s. It would be denoted as 5s. And then when we list out the substituents, it would be 5,8 dibromo 2-octine. For part B, question 1, we are given a reaction at equilibrium, and we're asked whether this equilibrium lies to the left or to the right. And for this type of problem, what we're trying to do is we're trying to find the direction of the reaction that favors the formation of a weaker acid and a weaker base. So first things first, let's list out what our Lewis acid and our Lewis base is and their corresponding conjugate acid or conjugate base. So we see right here that there is the first reagent to the very left has an anion, a negatively charged oxygen, and from our understanding of Lewis acids and bases, we know that especially for electron-rich sources such as negatively charged oxygen atoms, these tend to be Lewis bases. So we can describe this as a Lewis base, and we see here that there is also the second reagent. We see that it can qualify as a Lewis acid because it can accept an electron pair from this Lewis base. And correspondingly, when we look at the right side of the reaction, we see that we can describe this, the first compound to the right of the equilibrium, as being the conjugate acid, and the other reagent, the other product, as being the conjugate base. So with these types of problems, all you need is really just one piece of information. All you need is one piece of information and everything else falls into place. And in this case, it would either be finding out which base is weaker or which acid is weaker. And so let's look at bases. Right here, we see on the right that this is a salt, right? But a sodium salt. But this bisulfite anion, it is negatively charged actually. So if we were not considering it, if we just ignored the sodium cation, and we can compare that with this anion here. And the question that this boils down to is if there's a negative charge on the sulfur for the reagent on the right, and there's a negative charge on the oxygen for the anion to the left, the question is, does the sulfur contain a negative charge better, or does the oxygen contain the negative charge better? And what we know about this is that sulfur on the periodic table has a larger size. In fact, it's just one row below oxygen. And because of that, it's also more polarizable. And when an element is more polarizable, it's also capable of containing negative charge better. It's able to stabilize negative charge better. And if it's more stabilized, what this means is that it is also inherently weaker, right? The more stable a compound is, typically the more weaker it is. So if this is the weaker base, then this tells us right away that this is the stronger base. And also, it tells us that the Lewis acid corresponding to this conjugate base is in fact the stronger acid, because the strength of an acid is inversely proportional to the strength of the conjugate base, and the strength of a base is inversely proportional to the strength of its conjugate acid. So right away we can also find out that this conjugate acid here is the weaker acid. So what this tells us is, based on our previous discussion, is that this equilibrium indeed does go to the right. For question 2, we are given two Fischer projections, and we're asked to evaluate the stereochemical relationship between these two molecules that are represented by these two Fischer projections. So the most reliable thing to do is to assign the stereochemical configuration to the chiral centers in both of these projections. And we would do that by applying the CIP rules. So for the Fischer projection on the left, we can assign the highest priority group as the carboxylate group, because that carbon is attached to two oxygens, which is not the case for any of the other substituents. They're either, in the case of the substituent to the right, it is attached to an oxygen, but it's also attached to two hydrogens, which puts it at a lower priority as compared to a carbon atom that's just attached to two oxygens. So that would give this group the second highest, because it's still attached to an oxygen atom, while the remaining two are not attached to an oxygen atom. So when we compare this group here and this group here, what we find is that while this carbon here is attached to two hydrogens, this carbon is only attached to one hydrogen. So this gives this group a priority of 3, and this leaves the last one with a priority of 4. And if we were to draw the arrow denoting the direction in which the groups are going, this tells us that this would be given a configuration of R, and we don't have to worry about flipping it because the lowest priority group is not projecting out of the page, as you can see from the Fischer projection. So that gives us the configuration for the first one. Now let's look at the second one. Since we already know the priorities that were assigned to these groups from the last Fischer projection, we can just go ahead and write it down again, simply without having to think about how the rules are applied. And what we see is that we're going in this direction. So you might be tempted again to just put R like we saw in the last case, but watch out, the last priority group is coming out of the page, right? This group right here by the rules of the Fischer projection are coming out of the page. So we have to invert that apparent configuration to the actual one, which is S. So since this molecule only contains one chiral center, as you can see, because there's only one intersection in both of these Fischer projections, if the configuration of that one chiral center flips between Fischer projections, you can say with certainty that those two Fischer projections represent a pair of enantiomers. And that would be our final answer. For question 3, we're given the following substituted cyclohexane molecule, and we're asked to determine the number of methyl groups that are in the axial position in the more stable chair conformation. So when we look at this molecule, we can see that there are 4 substituents, 3 of which are methyl groups, and 1 of which is a tert-butyl group. And we know that tert-butyl groups are very bulky groups, and these bulky groups, if they're in an axial position, can cause 1,3 diaxial interaction, which is energetically unfavorable, and it leads to a pretty unstable chair conformation. So in fact, the most stable chair conformation you can have is one in which the tert-butyl group is in an equatorial position. And since all of these 4 substituents are pointing out of the page based on the wedge dash notation, that means that our tert-butyl group would have to be equatorial up. So I've drawn out this structure to the right where the tert-butyl group I placed as the one at the tip of this cyclohexane molecule, and I've drawn it in such a way that it is pointing equatorial up. And I've also drawn out the other methyl groups in a way such that they're also either axial up or equatorial up. And so if you look at this structure, what you find right away is that there are actually 2 methyl groups that are axial up, and there's 1 that is equatorial up. So that allows us to answer the question because we see that there are 2 methyl groups in the axial position. In question 4, we're given 3 resonance contributors, and we're asked in part A to place the contributors in order of increasing importance. So we want to find the order in which these contribute the most to that overall hybrid. So let's first start off by just seeing if any of these resonance structures contain an incomplete octet. For the structure on the left, there is no incomplete octet at any of the atoms. For the structure in the middle, there is an incomplete octet, and you can tell that by just drawing the arrows that denote the movement of electrons in these resonance structures. So we know that the electrons had to move to the nitrogen in order to get its formal charge down to 0. But what this cost was that the carbon ended up losing an electron pair, and now it has an incomplete octet. So we can go ahead and say that this has an incomplete octet. And if we try to draw the movement of electrons again, when we look at the structure to the right, we see that electrons had to move from the oxygen atom to the CO bond to form a double bond. And this caused the formal charge to go to a positive state, but at the same time, no octets were disturbed. So what I mean is that there's no incomplete octets. So right away we can say that the structure in the middle is in fact the structure of least importance, because if a resonance structure has an incomplete octet, it makes it very energetically unfavorable. It has less weight when you're considering the overall resonance hybrid. So now let's compare the structure on the left and the structure on the right. And what we see here, the main thing that differentiates these two is that there is a positive charge alongside a double bond on the structure to the right for the oxygen, and there's a positive charge on the nitrogen, which is double bonded to the carbon. And the question becomes, can the oxygen contain a positive charge better, or can the nitrogen atom contain a positive charge better? And looking at the periodic table, we can say that the oxygen atom is actually worse at containing the positive charge, because of the fact that it's more electronegative. So if we were dealing with negative charges here, the scenario would flip. The oxygen would be better because since it's more electronegative, it is able to stabilize the negative charge better as compared to nitrogen, which is less electronegative. But in this case, we're dealing with positive charge. And since the nitrogen is less electronegative, it's more electropositive. So it's able to possess positive charge in a more stable manner. So when you compare the two, it becomes clear that the nitrogen is a more stable one. So it's in fact the resonance structure of higher importance. So we can list this as 3, or the one that contributes the most, and the one to the right as being 2. For part B, we're asked to write down the hybridization of the oxygen atom in the box. And so the general guiding principle for a scenario in which an atom, it changes its formal charges, it changes whether or not it's doubly bonded to another atom, and so on and so forth. Whenever you're dealing with such changes, the thing to keep in mind is that the hybridization of that atom, in this case the oxygen, would be corresponding to the hybridization of the oxygen atom in the resonance structure where it contains the most number of double bonds. So in this case, that would be this third resonance structure to the right. So when we look at this third resonance structure, and I should add the lone pair, which is not shown here, what we find right away is that there's 3 electron domains, 1 single bond, and then 1 double bond, and then 1 lone pair. There are 3 electron domains, so this tells us that there is in fact an sp2 hybridization. And so just to reiterate, when you're looking at resonance structures and you're looking at an atom that is not always having the same hybridization, for all of the resonance structures, go for the one that has the most number of double bonds that are attached to it. So with that, we've solved question 4, part B. For question 5, we're given 2 carbocations, and we're asked to find out which one is more stable. Now, at first glance, if you look at this right away, you might be tempted to just say, oh, well, this looks like a tertiary carbocation, and this looks like a secondary carbocation. So yeah, I'm going to go ahead and just choose A as the final answer. But you have to be careful, because in this case, it's not as simple as that. Even though the carbon is, for carbocation B, that carbon is a secondary carbocation, you have to consider resonance again. Because in this case, the oxygen can donate a pair of electrons to that CO double bond, and that actually completes the octet of that carbon, so it no longer becomes a carbocation. And we end up getting a positively charged oxygen in place of that. But in this case, the oxygen still has a complete octet. So if you're comparing a stable compound, a compound that has no has a complete octet as compared to a compound that has a incomplete octet, you can tell right away that that compound is going to be more stable. The compound that doesn't have that has all its octets filled. And we saw a similar scenario in the last problem, right? The structure that has a complete octet is always more favored over a structure that has incomplete octets. So this actually ends up giving B as our final answer. So be careful when you reach these types of problems. Always look out for resonance. In part A, there's no way that you can actually do resonance because the lone pairs on the oxygen atom can't go down to a CO bond, or it can't actually reach this CC double bond without having to break bonds or having to exceed the octet limit. So just keep that in mind when you approach problems that are similar to this. For question 6, we are given two reactions, and we're asked to compare the reaction rates and determine which reaction is faster. So when we look at these reactions, and if we're trying to determine which one goes faster, we need to first determine what type of reaction this is in the first place. So when we look at our reagents, we find that there is the nitrile anion, which is a good nucleophile, and we find that there's a solvent for both of these, which I'll put this in a different color. This is acetonitrile. And acetonitrile, if you draw out the Lewis structure, is a protic solvent. And the fact that we have a good nucleophile, the nitrile anion, and acetonitrile, a polarly protic solvent, it should give you the idea that we're actually dealing with SN2 reactions. So SN2 reactions. And when it comes to SN2 reactions and their reactivity, we know that these reactions very much favor a primary reacting with a primary alkyl halide as compared to a secondary alkyl halide, and it reacts with the secondary halide much better than a tertiary halide. And the reason for this, just as a recap, is because of less and less steric hindrance as you go from tertiary to primary. So since this is a concerted reaction, it all occurs in one step. So what this means is that we have to make sure that the nucleophile isn't hindered by a lot of blocking groups that can cause a steric hindrance. So when we look at these two, we see that this is the carbon that is attached to the bromine is a tertiary carbon because it's attached to 3 other carbons. And the carbon attached to the bromine is a secondary carbon. So right away we can tell that in fact a B will be more favored because it's a secondary alkyl halide, so it will react faster, and it virtually won't react with the tertiary alkyl halide. For question 7, we are given 2 pairs of compounds, and we're asked which technique, NMR, IR, or mass spectrometry, will most readily allow differentiation between the compounds in each of these pairs. So let's look at these compounds. For the first pair, we see both of them are cyclohexane molecules, but one has a bromo substituent and one has a chloro substituent. And trying to differentiate between these two by, say, IR would be a difficult task, because even though one has a carbon-bromine bond and the other one has a carbon-chlorine bond, you can't really differentiate between these two in IR because the stretching frequencies for these two types of bonds are within the fingerprint region, and they easily overlap with each other. So it becomes very hard to differentiate between these two compounds via IR spectroscopy. So then a good option would actually be to consider doing mass spectrometry. And the reason is that in this molecule, everything is in these two molecules, everything is the same except the fact that they're just different halogen substituents. And bromine has a higher atomic mass than chlorine. And because of that, this difference can easily be spotted out in mass spectrometry. So this is why mass spectrometry would be able to easily differentiate between the two, because of the fact that that's the only difference in mass. So we don't have to go and find out the chemical structure, which is what IR would allow us to do. We just have to see the mass difference and assign the one that has a reading for higher mass to the one corresponding to the bromine, and the reading corresponding to the lower mass to the cyclohexane molecule with the chlorine substituent. So with that in mind, we can say that this can be easily detected via mass spectrometry. For part B, we are given two compounds that have very apparent differences in their functional groups. So for the first one on the left, we see that there are two ethers, and on the one to the right, we see that this is technically a carbonate group, but it can also be treated as two esters. So when we look at this, we see that there are apparent differences in their functional groups, and IR is the technique to go when you're just trying to detect a difference in functional groups, because it's way more convenient to use that as compared to NMR when it comes to identifying these functional groups for these two groups in particular, because if you look at the stretching vibrational frequencies for the CO bond, this is around 1,000 wave numbers, and the carbonyl carbon and the oxygen in that carbonyl group, the stretching vibrational frequency is around 1,700 wave numbers. So you can tell right away which one is which one is which, because there will be a clear evident peak at 1,700, which will correspond to this compound right here. And if that's not present, then we know among our choices that it has to be this molecule. So with that in mind, we can easily use IR as a way of differentiating between these two compounds. It's very quick. NMR, you can do the same thing, but it's not as quick and convenient as just running a quick IR scan on this mixture of compounds. For question 8, we are given a set of compounds, and we're given an IR spectra, and we're asked to find the compound that corresponds to that IR spectra. So when we look at this IR spectra, let's try to identify the main peaks. So we see that there is a peak right before 3,000, and this corresponds to the CH bond, the CH stretching vibrational frequency, the CH stretching frequency. And also we see that there is a peak corresponding to a carbonyl carbon, right around 1700, as I had shown in part 7. So, in question 7. So, let's look at our choices. For part A, it's showing that there is a hydroxyl group attached to this compound. When we look at the IR spectra, there's no indication that there is an OH bond, because if there's an OH bond, we typically anticipate some large, broad curve after after 3000, and this curve typically corresponds to the OH bond. It always corresponds to the OH bond. So, since there's an absence of that group, we can right away eliminate A and D as our choices. And we eliminate D because this carboxylate group this carboxylic acid has an OH group attached to it, and that would be present in the IR spectra if that was the molecule being examined. So we're left with choices B and C. And when we look at the IR spectra, we actually can't find any peaks corresponding to the stretching of the NH bond, because that occurs around 3300 wave numbers. We don't see anything like that in the IR spectra. And that means that for part B, where there are NH bonds, this would not actually represent the IR spectra. This would not represent the molecule for which this IR spectra was done. So this cancels out B, and it leaves us with C as our final answer. And that makes sense because in C, the only two types of bonds that are present are CH bonds and the carbonyl CO bond. So that leaves us with C as our final answer. For question 9, we are given the following molecule, and for part 1, it asks us under, pay attention to this, normal conditions of purity, what are the theoretically predicted multiplicities of the signals for the protons labeled A, B, C, and D? So when you're considering normal conditions of purity, right, let's discuss that first. When you're talking about normal conditions, that means that certain types of coupling will not be counted when we are trying to find out the multiplicity of a certain proton. And I'll explain what I mean in just a bit. So let's just go ahead and start assigning multiplicities for the molecules for the protons of interest. For part 1, the first option is multiplicity. The first question is multiplicity of A. So for this proton, it is attached to a carbon which is double bonded. So this proton is actually not chemically equivalent to this proton. They're not chemically equivalent. So that means that it is indeed possible for A to engage in spin-spin coupling with this proton. So by the n+1 rule, right, the number of protons that you're actually splitting, you're doing spin-spin coupling with, plus 1 gives you the multiplicity. And so in this case, we have one other proton that we're doing spin coupling with, plus 1 gives us 2. So we can write down 2 for the multiplicity of proton A. For proton B, we are in a position where the carbon atoms adjacent to this carbon, so it would be this carbon right here and this carbon right here, there are no hydrogens that are attached to those carbons. And since we're dealing with a carbon that's just singly bonded to the other carbons, there's no double bonds we don't have to worry about the issue of spin-spin coupling, either with protons for adjacent carbons because there are none, or even protons for the same carbon because we're not dealing with a carbon that's doubly bonded. So what this tells us is that, in fact, by the n+1 rule, we have 0, a multiplicity of 1. So we get a multiplicity of 1. Now, for proton C, this gets a little trickier because now we are getting spin-spin coupling, but with different types of protons in different that are chemically not equivalent. So multiple types of protons that are not chemically equivalent. So for this proton here, the corresponding carbon is this, and it's attached to 3 other carbons. These hydrogens here are actually chemically equivalent, right? But the protons here are attached to this carbon, which is attached to this ring. And so it's in a different chemical environment. So we actually get complex splitting. So what that means is that when we're trying to evaluate the multiplicity, we would have to multiply 2 sets of n+1. So for the 2 methyl groups that are attached to this carbon, the carbon for proton C, there are 6 chemically equivalent protons, right? So that would be 6 plus 1, but we're not done yet. Now, let's consider the protons for this carbon right here. These have 2 chemically equivalent protons. So if we write that down, there would be 2 chemically equivalent protons plus 1, and this gives us 7 times 3, which is just 21. So there would be a multiplicity of 21. So please be careful when you're in this type of scenario, because you don't just use n+1 to get your final answer. If there are different types of chemically equivalent protons that are interacting with your proton of interest, you're going to have to multiply the products of n+1, and each of those terms would correspond to a different type of chemically equivalent proton. So just keep an eye out for that. And now we reach the interesting case, part D. Part D, we have carbon that is attached to 2 protons of its own, and if we're trying to evaluate the multiplicity, we see that it's also attached to a carbon that has 2 chemically equivalent protons of its own. But also, that carbon is attached to an oxygen, which has a proton. So the question is, well, do we consider these 2 types of, because just as in the case for when we're trying to evaluate the multiplicity of C, should we take a product of 2 different types of n+1 corresponding to 2 different types of chemically equivalent protons? Or do we just ignore the proton for this OH group and move on? Well, this is where the difference between purity comes in. So for part 1, it gives us normal conditions of purity. And under normal conditions, actually, the protons that are attached to heteroatoms such as oxygen don't really engage, are not, at least per the NMR spectra, are not shown to be engaged in spin-spin coupling with our proton of interest. It's not shown, so you can just kind of turn a blind eye to it. But when you're dealing with ultra-pure conditions, then it can actually detect the spin-spin coupling contribution that's done by this proton. So what this means for us is that for this question, right, for 1, we turn a blind eye to that proton that's attached to the oxygen because we're in normal conditions. And if that's the case, we see that there are 2 protons attached to that carbon, to the adjacent carbon, chemically equivalent protons. So by the n+1 rule, since there's no fancy splitting, it just gives us 2 plus 1, 3. So our multiplicity would be 3 in normal conditions. But now let's go to ultra-pure conditions for part 2. Here we are given a proton. Now we have to consider the proton that's attached to the oxygen. So now we have to play the same game that we did when we were considering the multiplicity of proton C. So in order to do that, just like earlier, let's take into account the 2 chemically equivalent protons attached to the carbon adjacent to the protons in position D. And let's also take into consideration that single proton from the OH group. So that would be 1 plus 1. And this gives us 3 times 2 is 6. So that would be our multiplicity. That would be our final answer. Now we are in part C, which is overreactions. So for question 1, we are given cyclohexane with a methyl substituent in excess, and we're given the following series of reactions, and we're asked to get the final product. So let's go right in. So for the first reaction, we have bromine along with light. And obviously bromine and light is a very quick, spontaneous, and chaotic process in which bromine radicals are formed. And as a issue, if you produce a lot of bromine radicals and there's a low concentration of our substrate, which is in this case this molecule right here, well, what happens is an issue called polyromanation. You end up having so many bromines per molecule, so you have a bromine here and a bromine here and a bromine here. You end up having way too many bromines. So that's why we have we add an excess amount of this reagent to avoid that problem, and we end up just getting 1 bromine substituent added to this molecule. So if we go ahead with the first reaction, step 1, if we think about it, you can kind of think of this as having 2 bromine radicals, right? There was a bromine bond, but then under the presence of light, it underwent homolytic cleavage, or the splitting of the bond, to produce 2 bromine radicals. And 1 bromine radical will end up abstracting the proton that was originally attached to that carbon. And the reason why is because it forms a tertiary radical. And tertiary radicals are among the most stable radicals that are there. So when you form that tertiary radical, another bromine radical comes in and reacts with that tertiary radical to form a new CBr bond. And this gives us the following. So that's what we get when we do step 1. In step 2, we have sodium ethoxide in ethanol solution, and we have to ask ourselves, what type of reaction is this? Well, if I ignore the sodium and just look at the ethoxide anion in solution, we know that the ethoxide ion is actually quite a strong base, and it can actually allow us to do an E2 elimination. So in this scenario, our alpha carbon is this carbon right here, but our beta carbons, the carbons adjacent to the alpha carbon, are here, here, and here. But obviously we want to produce after doing the elimination reaction, we want to produce the alkene that is the most substituted since it's the most stable. So if we do that, if we take that into consideration, let me just write down that this is an E2 reaction. We end up finding the following. And now we've completed step 2. For step 3 and step 4, we actually undergo a process known as ozonolysis, and alongside a reductive workup. So what this does, steps 3 and 4, is that it will cleave this double bond. And if that carbon is, say, if this carbon right here, it's attached to one methyl group, right? So it will actually create a CO double bond, and since that carbon is already attached to 2 other carbons, right, it will actually form a ketone on this end of the molecule. But on the bottom half, there's a carbon atom, the other side of the double bond, there's a carbon atom that's attached to a hydrogen and a carbon. So in this case, it will actually produce an aldehyde. So taking that into consideration, we can actually break this chain and form a new compound. A new compound, but it's no longer a cyclic compound is what I meant to say. You form an acyclic compound, and we can write that out as so there are 1, 2, 3, 4 carbons that are not involved in double bonding. So we can just express them as a chain of methylene groups. And we go from here, from this position all the way to this position, and we draw out the next carbonyl group. But in this case, as I mentioned earlier, this is an aldehyde. Now we've reached we have one more step to go, and in this case, an acetylide ion reacts with this compound in excess, and then it has a reductive workup. So I'll show what actually happens here, because this is the anion, and because of the fact that it possesses a negative charge, it is capable of acting as a strong Lewis base, in which the electrons will actually interact with the positively charged carbonyl carbon atoms, and this will cause the electrons in that, it will cause the double bond, the CO double bonds, to no longer be present, as the electrons will move up, and this will form negatively charged negatively charged oxygens, and it will also result in adding 2 acetylide groups to both ends of the molecule, and ultimately after we add acid to turn those negatively charged oxygens into OH groups, we get the final product, which is as follows. Just going to write out the CH3 group with the methyl notation. So we see here that the anion has basically bonded with the carbon on both ends, and we still have, and the oxygens after they underwent reductive workup became OH groups, and the original methyl and the hydrogen substituents are also present. So this gives us our final answer for part 1. For part 2, we are given this molecule, this alcohol, and it undergoes 2 steps. In the first steps, it reacts with PBr3, and in the second step, it reacts with a reagent in DMSO. And so in order to go about and solve this problem, we have to understand again what type of reaction are we dealing with. So in the first, when we're dealing with PBr3, PBr3 is used to convert alcohols into alkyl bromides, and it does so using an SN2 mechanism. And from what we know about SN2 reactions lead to a backside attack and an inversion of stereochemistry. So basically, whenever you go through step 1, the OH group ends up going, and you end up inverting the stereochemistry of that carbon. So like a backside attack, the bromine would be on the other end, opposite to the OH group, which is what is leaving, and the hydrogen substituent would also switch its orientation from going into the page to going out of the page because there's an inversion of stereochemistry. So that's the first step. In the second step, we react this salt in DMSO with the substrate. And the important thing to realize here is that this is a strong nucleophile. And so what it will do is it will also go through an SN2 reaction. So again, the whole procedure repeated, we would go through a backside attack, and this ultimately results in the following final solution. So this is our final answer for question 2. So make sure to be careful about the stereochemistry because you're inverting it, and in this case we're inverting it twice because there's 2 SN2 reactions. And on an additional note, one thing that might have helped you in identifying that this second step was an SN2 reaction is also that we were using a polar aprotic solvent. So DMSO is indeed a solvent that would be suitable for an SN2 reaction. For question 3, we are given this compound, and in the first step, it reacts with sulfuric acid in heat. So the first thing to realize is that if you have an OH group in your compound, it is very sensitive to being attacked by an acidic reagent and forming water. And that's precisely what happens in this case. We form the following. Water is basically attached to this molecule now, and it's very stable. Once it leaves, it's a very stable leaving group, so it will leave on its own. And what this leaves us with is a carbocation, a secondary carbocation. Now, we're not finished yet though, because we're given a good indicator that there is going to be elimination because there is heat. And the elimination type we're dealing with is E1 because there is the formation of a carbocation. So we can use a counterion that we just recently produced, which was this ion, because this ion was formed after H2SO4 reacted with the molecule, and once an oxygen atom interacts with a hydrogen that's adjacent, this will result in the migration of electrons to form a double bond. And now that we're at this state, we've finished the first step. But now, here comes the next part, NBS with light. So as a recap, NBS is just a way to provide bromine radicals at a lower concentration to prevent the issue of polybromination, and especially around double bonds, because if we include bromine with light, there's a very good chance that it will result in the addition in an addition reaction in which that double bond is no longer present. So when we add that NBS, we can think of it as bromine interacting with a proton. And in this case, we are reacting with this proton in particular because it will result in the formation of an allylic radical. Excuse me. Okay, so the more interesting thing is that it will result, since it's an allylic radical, it can have resonance. And when we draw out the resonance structures, we see sorry about that. Well, basically this radical migrates and it results in another resonance structure in which let me see if I can draw it correctly without it auto-correcting. Okay, there. So this radical goes up here, and that's how we get that other resonance structure. Well, now that we have two resonance structures, and we still are in a radical bromination reaction, we can react these two resonance structures with bromine radicals, and it gives us the following final answer. So that is how we would solve question number 3. For question 4, we are given a tertiary alkyl halide and specifically a tertiary alkyl bromide, and we're given the reagents of methanol in heat. And so the first step, as usual, is to identify what type of reaction this is. So when we look at our substrate, we see that, again, it's a tertiary alkyl bromide. So also when we see that there's also heat included, we can think of elimination, right? So there is a good chance that we're dealing with an E1 reaction. But also, when we look at our substrate, we see, our reagent, we see that since it's methanol, it is not a strong base. And for an E2 reaction, right, E2 reactions require strong bases in order to get started. Since we are still doing elimination and E2 isn't an option either, we're left with E1. And this checks out because E1 reactions have to work well with tertiary alkyl halides because of the formation of a stable tertiary carbocation. So now that we have identified that, we can go ahead and begin, but also with one more note. Since there's E1 reactions, since a carbocation is being formed in this process, there's also SN1. And SN1 reactions in this case would actually dominate. And it seems counterintuitive because we're applying heat, but if you really want E1 to be favored over SN1, you have to choose you can choose a acid that has a weakly nucleophilic counter ion alongside heat. And in this case, there is the case of methanol. Methanol is a slightly acidic compound, but whenever you deprotonate it, it results in a methoxide ion. And a methoxide ion is very nucleophilic. So in this case, having this wouldn't really go in favor of an elimination reaction because an elimination reaction, the E1 reaction, would require a counterion that's not very nucleophilic. And the counterion of methanol is methoxide, which is very nucleophilic. So in this case, that would mean that the SN1 reaction would predominate. And this is an important fact that we're going to have to keep in the back of our heads as we go along with this process. So let's start off by deprotonating this alkyl bromide. Not deprotonating, excuse me. Removing this bromine group, and forms the tertiary carbocation. And now we are at a junction because it can result in two different possibilities. Either we can interact with we can either do substitution, SN1, or we can do E1. And so let's first just go for the easiest option, right? E1. E1 would involve methanol actually taking a proton from the adjacent beta from the beta carbon. That would result in the migration of electrons, resulting in the formation of a double bond that's actually tri-substituted. So this would be represented as this. As I had mentioned earlier, the E1 product is minor because we don't have a strongly nucleophilic counterion for the methanol reagent. So now let's consider the major product, the substitution product. In this case, the methanol, let me do this in another color because otherwise it will be confusing. It will form a bond with that tertiary carbocation. And after the removal, so we can, let me just, it just needs one more thing, in that another methanol molecule will come in. It will take that additional proton to make that positive charge go to 0, and we end up with an ether. So this would be our major product, and that would be how we would solve question 4. For question 5, we are given this compound, and we see that it is a geminal dihalide, and what that means is that there are 2 bromo groups attached to one carbon here, and the first step involves reacting this compound with potassium hydroxide at 200 degrees C. And we know that potassium hydroxide is a strong base. We know that for sure. And so this will allow us, also at high temperatures, favoring elimination in this case, because we're dealing with a very strong base, we are going to form an alkyne. And the reason why is because there are 2 bromine groups, right? And if both of these bromine groups were removed via elimination, it would result in the formation of an additional pi bond. And that means that we end up forming, if we remove both of these, if we remove one of them, we form a double bond. But if we remove 2 of them via elimination, we form a triple bond, or an alkyne in this case. So we'd be tempted to just go ahead and put in an alkyne right here. So if I draw it out, you might be tempted to just go ahead and draw in an alkyne, so a terminal alkyne, because it's attached to the last carbon. So you would think that, oh yeah, it should form a terminal alkyne. But in fact, the case is that we are not forming a terminal alkyne. And in labs, what they often observe is that even though they might be trying to form a terminal alkyne, at higher temperatures, the alkyne might actually move around, and it will actually end up becoming an internal alkyne. So you'll end up moving one bond inwards. And at lower temperatures, they end up seeing the terminal alkyne that they're looking for. But at higher temperatures, you actually end up resulting in the formation of internal alkynes. So this is a thing to just keep an eye out for, because it's a very easy place to mess up at if you're not careful. So what this actually would be, if we move one bond back, so initially we were thinking of a terminal alkyne here. If we just don't look at those two bromine groups, we were anticipating an alkyne group here, but at higher temperatures, actually, this shifts inward by one bond. So what we get is actually this compound. And now the next step is to react this compound with H2 and this mixture of reagents, which is actually referred to as Lindlar's catalyst. So in step 2, basically, we're going to be hydrogenating, or doing an addition reaction on that triple bond. And we had to be careful about this because it does it in a way that the hydrogens that are added to each side through this addition reaction are on the same side of the double bond, and this is referred to as syn addition, SYN. So this is where we get to after we apply hydrogen and Lindlar's catalyst. Now the last step is to apply this mixture of reagents and see what we get. And in this case, it turns out that this is actually referred to as a carbenoid. So it's very similar. It's similar to a carbene, which is denoted by Cr2. Even though it's not the same as a carbene, if you include a base such as potassium hydroxide, it can effectively serve as a carbene in its functionality. So what it will do is it will actually form a cyclopropane substituent. So it will result in an addition reaction in which we end up with a single bond, and in the middle of these two carbons, there's a cyclopropane ring that's formed, which contains two bromine atoms at the top. So let me draw it out for you. And since we're now removing all the possible double bonds and multiple and extra bonds, and we just have sigma bonds now, we have to take stereochemistry into account by including wedge dash notation. So since the hydrogen atoms were on the same side, and these two groups were on the same side of the double bond, since the since the cyclopropane ring will be formed in between this bond, we have to make sure that both of those two sets of groups are on the same side when we are writing it out. So let me just draw it to clarify what I'm saying. So there's no longer a double bond, just a single bond, but now there is a cyclopropane ring that also has two bromine groups attached to the top of it. And you can apply the same logic if you used CHCl3 or some other halogen, because the same mechanism applies. So make sure to look out for carbenoids, because they will result in the formation of cyclopropane type rings. And with that, we've solved question 5. For question 6, we are given this carboxylic acid, and there's 2 steps. In the first step, it reacts with propanol in acidic solution. So let's see what happens. So it turns out that when you're reacting an OH containing group with another OH containing group, in this case carboxylic acid with a alcohol, and you're doing it in an acidic solution, you actually end up forming an ether. So let me write it out. Sorry, not an ether. I meant an ester. My apologies. This is an esterification reaction. And now the next step is a Grignard reaction, because you see here that there is the Grignard reagent, some sort of substituent, organic substituent, followed by MgBr, which is a Grignard reagent, and then afterwards accompanied by H3O, which is essentially a reductive workup. So just converting any sort of anion, such as a negatively charged oxygen atom, into an OH group. So if we were to apply this Grignard reagent to this ester, right, it actually turns out that in the first, since this is in excess, we can do this several times. And this is what will affect our final product, applying it in excess. So I'm just going to denote this group by, actually no, never mind. That will not be necessary. So this Grignard reagent, right, when it reacts with this ester, what you end up forming is essentially, it's a carbon-carbon bond forming reaction, right? So electrons will shift to that carbonyl carbon, and it will result in the migration of electrons to that oxygen, and it will produce an unstable intermediate that will be negatively charged, and the electrons will come back down, and it will actually end up removing this group right here. And ultimately, what this gives us is, this is essentially what we get. But we're not finished yet. Now let's add one more. because we can keep on going until we form an alcohol. So if we do this again, we end up with an unstable intermediate, which I will draw it here, not like last time. Running out of space, so that's why it's a little. And lastly, our cyclopropane. Now the last thing that we need to do is just reductive workup. So we're just gonna, that negatively charged oxygen is gonna react with the acidic solution and it's going to form a alcohol, or sorry, an OH group. Apologize, my pen keeps on autocorrecting this. Okay. There you go. So this is the final answer to question number 6. For question 7, our compound of interest goes through 3 steps. In the first step, it undergoes dihydroxylation with the help of osmium tetroxide, hydrogen peroxide, and OH minus. So what that means is that just like in the previous case, in a previous question, we had used hydrogen and Lindlar's catalyst to reduce the to do an addition reaction, on the alkyne to add hydrogen atoms on either end via syn addition. The same logic applies here when we're doing this dihydroxylation reaction. So if we apply the same logic here, instead of adding hydrogens, as you would see for the Lindlar's catalyst, hydrogen and Lindlar's catalyst, what we end up doing is we actually end up adding OH groups, which are, again, syn addition, so they add on the same side of the of the ring, and that would result in the methyl group on the other side of the ring. In the second reaction, what ends up happening is that we are doing oxidative cleavage with HiO4. So oxidative cleavage in this case just means that since we have 2 OH groups here, we're going to actually break this sigma bond, and we're just going to end up forming 2 carbonyl groups, 2 carbonyl substituents for this ring. And I will show you what that means. So basically, prior to adding periodic acid or HiO4, this carbon, oh no, excuse me. Okay. this carbon right here was attached to, aside from the OH, it was attached to this carbon and the carbon from the methyl group. So when the cleavage occurred, it ultimately resulted in the formation of a ketone, as you can see here. On the other end, you see that this carbon right here, it was only attached to a carbon and a hydrogen. So when this cleavage occurred, it ended up forming an aldehyde. The last step is to apply lithium aluminum hydride in excess along with reductive workup, or adding H3O+. So what this does is that lithium aluminum hydride is a very strong reducing agent, and that means that it can convert a aldehyde into a alcohol, and it can convert a ketone also into an alcohol. So if we keep that in mind, alongside doing a reductive workup, what we end up getting is the following as our final answer, because these two CO double bonds essentially just are reduced to alcohols, or to OH groups. And that is how we get our final answer for question 7. For question 8, we're given this alkene, this branched alkene, and there are 3 steps. For the first step and the second step, it's actually, these 2 steps are part of the hydroboration oxidation process. And in this process, essentially, you are adding after the first reaction, you form a BH2 carbon bond, and via anti-Markovnikov addition, and after the second step, you also end up forming, you remove that BH2 group and you replace it with a hydroxyl group. And this is a good way of forming alcohols from alkenes in particular. So steps 1 and 2. Hydroboration, oxidation, and just as we had seen with the dihydroxylation reaction and with Lindlar's catalyst, this type of addition is also syn addition. So you're adding it to the same side. And in terms of the regiochemistry, or how the addition reaction occurs, which parts of the reagent go to which side of the double bond, this is anti-Markovnikov addition. So if we were to add which side would we add the OH group to? This side or this side? Well, according to Markovnikov's rule, we would add the H on this side. But since we are doing anti-Markovnikov, we would actually add the H on this side, and we would add the OH to this side. So what this means is that when we write out the product of this sequence of reactions, we end up with the following product. The OH was added to the side that actually had more hydrogens, and this is how anti-Markovnikov addition works. So the last step, step 3, maybe I should write it here. Is this? Okay. Step 3, we have sodium dichromate, sulfuric acid, and water. And this combination of reagents is known as the Jones oxidation reaction. And the Jones oxidation reaction is a very strong, the reagents involved result in a very strong oxidation reaction in which a alcohol like this can be immediately converted into a ketone. And that's what we see. So that is our final answer for question 8. For question 9, we are given pentanol actually, and we're given 2 steps. The first step is simply to react this alcohol with sodium. And in this reaction, what forms is actually simply the formation of an oxygen anion balanced by the sodium cation. And this is good because now it will allow us to proceed with the next step reaction, in which we react this with propyl bromide. And as you can see, this negatively charged pentoxide anion can serve as a good nucleophile in an SN2 reaction. And so it can interact with this alkyl halide, result in a backside attack, ending up removing that bromine leaving group, and you end up forming an ether. In fact, this process is known as the Williamson ether synthesis. And with that, we have solved question number 9. For part D, we are given a mechanism problem, and in this reaction, our initial reagent reacts with sulfuric acid at 100 degrees C to produce a new product. And the question is, what is the first step that we have to take in order to get from point A to point B? And that answer lies in trying to just look at the structure of the final product and compare it to the initial product. When we look at the final product, we see that it is a ring composed of 4 atoms. When we look at the initial reagent, it is a ring composed of 3 atoms, 3 carbon atoms. So the only way to get from 3 to 4 carbon atoms, 4 carbon membered ring, is through a ring expansion reaction. And that means forming a carbocation at a carbon adjacent to the ring. Carbon adjacent to the ring. So if sulfuric acid is going to go right ahead, being the acid that it is, and react with one of the OH groups, which one would it be? Well, in order to form a carbocation at the carbon adjacent to the ring, which is this carbon right here, we would have to attack this OH. So if we go ahead and do that, if we draw out all the notation, we see that this oxygen will donate its electrons to that proton, and that bond with the oxygen will dissolve, form HSO4 minus, which will come in handy later. So this gives us the following structure. Obviously, water being the stable leaving group that it is, it will leave, and this will result in the formation of a tertiary carbocation. Now we're in a position to do a ring expansion. So if we did a alkyl shift, right? If this pair of electrons that's originally connecting these two carbon atoms moves up by one, then what we get is our desired compound. And there would be a positive charge at this carbon, which corresponds to this carbon. Oh, my bad. I apologize. I did not include the movement of electrons there. Now we have our four-membered ring, but we're not finished yet, because now we have to go from that. We have to first of all remove all the positive charge, and we also have to form a carbonyl bond. But to address the issue of there being an incomplete octet at this carbon, we can simply resort to resonance, because this oxygen has lone pairs that it can donate to fill that missing octet. And when it does that, we form our carbonyl bond. Now the last issue is the positive charge. So, as I mentioned earlier, the HSO3 or the water that is formed can come in handy at this step. So the water that we had produced earlier from that leaving group, or the HSO4 minus. So let me in either scenario, right, it will deprotonate, or in the case of water, and either or, and this results in the movement of electrons back to the oxygen, which, oh, excuse me, I realized I had made a mistake earlier with the formal charge. Positive charges on the oxygen. So as the electrons move back, now we have our final product. So this is how we would go about with the mechanism. In part E, we are given a synthesis problem, and it says to synthesize the molecule below using any of the following reagents: alcohols or alkenes of 4 carbons or less, any other inorganic reagents, and any oxidizing or reducing agents. So let's go ahead and do retrosynthesis on this molecule to try to reduce it to alcohols or alkenes of 4 carbons or less. So in the first step, and just as a note, for the purposes of time, I had worked out this problem, but I will go through this step by step and how we would get to our final answer. So the first thing we need to do is when we see this structure, one of the first things that can be cleaved, at least you can kind of mentally cleave it, is this CO bond right here, because what we have here is actually an ester. And there is, obviously from the requirements of the problem, there is no alcohol. I mean, we're only allowed to have alcohols or alkenes of 4 carbons or less. So having an ester is already, something way out of what our requirements are. And it's actually possible to do an esterification reaction to get to this product. And if we represent it as an esterification reaction, we can actually produce this product, this final product, from these two initial reagents. So you had actually seen this reaction earlier in a previous problem when I described an esterification reaction, and this is referred to as the Fischer esterification reaction. And the mechanism for this is not as easy as it seems, but that's another story. But for forming this ester, right, one of the two things you need are a carboxylic acid, and you need an alcohol that will serve as that component of the ester that follows the carbonyl carbon. And if you add acid, you end up forming the final product. So that's how you would that's how you go back one step retrosynthetically. So especially if you see any sort of CO bond, take that into consideration when you're trying to do your retrosynthesis. The next step would be, since we see that there is a carboxylic acid, and carboxylic acid is really the most oxidized state that a carbon can, one of the most oxidized states that a carbon can be in, you know that there's some sort of strong oxidizing reagent involved. If you want to go from, say, an alcohol to a carboxylic acid, it requires some real power, and that's what the Jones oxidation provides. The Jones oxidation is a very strong oxidation reaction. So you can actually go back one step retrosynthetically and get back to an alcohol. And that's precisely what you see here. So we worked one step backwards. And before I forget, since we are dealing with, I forgot to address this reagent, but this reagent, since it is a alcohol of 4 carbons or less, it checks off. So we don't need to go backwards retrosynthetically anymore for this particular reagent or this part of the process. Now, for this compound, it still doesn't match our criterion that the problem gives us. It is an alcohol, that is true, but it's not an alcohol of 4 carbons or less. So we need to break down the structure more. So that means that we're going to have to form carbon-carbon bonds in order to get to this point from simpler compounds. So that means we're going to have to use some carbon-carbon forming reactions, and that's precisely what we get. We can actually use a Grignard reaction to get rid of the branched carbon at this point. And if we do that, if we instead, in the place of this carbon, if we place a MgBr to get us to a Grignard reagent, and alongside a carbonyl carbonyl compound, which is in this case formaldehyde. Now we are breaking it up slowly. So now we have two retrosynthetic paths to go down. We want to reduce this first down to an alcohol. And this is quite simple actually, because an oxidation reaction to convert to an oxidation reagent that we can use is PCC. PCC, instead of a reagent such as the Jones oxidation reagents, is a much milder reagent. It doesn't immediately convert an alcohol into a carboxylic acid. No, it just converts a primary alcohol into a aldehyde. And in this case, since we're dealing with methanol, we would convert that primary alcohol into formaldehyde. And so PCC, just keep this in your mind, PCC is definitely, it's just like when you're dealing with sodium borohydrate and lithium aluminum hydride, which are both excellent reducing agents, but lithium aluminum hydride is the stronger reducing agent compared to sodium borohydride. In the same manner, if you're comparing PCC and Jones oxidation is a much stronger oxidation reaction as compared to the PCC reaction, which allows you to convert primary alcohols to aldehydes without having to worry that it's going to go too far and convert to a carboxylic acid. So that's just something, now that we've basically retrosynthetically gone back to a simple alcohol, which is less than 4 carbons, which is methanol. So here is another starting point. So far we've identified 2 starting points. We've identified butanol and methanol. Now, since we have the Grignard reagent, we know that the criterion don't mention a Grignard reagent as one of our starting points. So we have to go backwards, and we have to consider the reaction that allows us to form a Grignard reagent from an alkyl halide, because that's how Grignard reagents are formed. And if that means that we would basically be left with this compound, we consider the Grignard reagent formation reaction, which is reacting a alkyl bromide with magnesium and diethyl ether, which is also Et2O. So now we're at the alkyl halide, but still that doesn't match our requirements. So we know that this is a bromination reaction, and since we're looking for alcohols, right? Alcohols can be converted to bromides by using PBr3. And this is a reagent we saw before in a previous problem, which allowed us to convert an alcohol into a alkyl bromide. Now we're at this point, and we have an alcohol, but still it doesn't match our requirement of an alcohol of 4 carbons or less. So we're going to have to go one more step further, and we're going to have to do include another carbon-carbon formation reaction in our retrosynthesis. So notice what I'm doing here. Every step, I keep on looking back at the criteria that is required for the starting materials. If my particular compound, the compound that I'm at in my retrosynthesis, if that matches the criterion, then that's good. We reached our starting point. Otherwise, we have to keep on going backwards. So that means we're going to have to involve another carbon-carbon formation reaction, which in this case is again another Grignard reaction. And in this case, we are basically going to split this alcohol, this branched alcohol, alcohol down the middle. Oh, excuse me. And we can split that into a aldehyde and basically another Grignard reagent, but this time both of them involve 4 carbons or less, so that is good. And now it gets easier. So now we're at this aldehyde, and again, PCC is the way to go if you're trying to convert from an alcohol to an aldehyde. So if we use PCC, we can get back to our final an alcohol, which is actually 4 carbons, butanol. So we reached one starting point, but now we have to reduce this Grignard reagent as well. So involving the reaction that's used to form Grignard reagents, magnesium and diethyl ether, we get to an alkyl halide. And this alkyl halide, again using PBr3, can be formed by using a PBr3 and a simple primary alcohol, which in this case is propanol. So if we look back now, we see that we first started off, one of our first starting reagents that we came to was butanol, then methanol, then butanol, and propanol. So when you're faced with these synthesis questions, always make sure to go one step at a time and ask yourself the question, am I matching the criterion that they ask me for the starting materials? If so, I'm good. If not, I have to keep on going backwards and backwards and backwards until we get to our desired point. So this is how we would go about and solve this problem. For part F, we are given the following question. A compound with the formula C8H10O exhibits the IR and proton NMR spectra shown below. Please identify this compound and draw the structure in the box provided below. So with this type of question, our goal is to determine the molecular structure as noted in the problem. But the first thing we have to do, right, before we jump in and start trying to read the IR spectra or the NMR spectra, is to determine the degrees of unsaturation. So let's go ahead and do that, because this will tell us the sum of the number of multiple bonds, so double bonds, triple bonds, things of that sort, or rings, the sum of multiple bonds and rings. And this is a valuable tool in helping us to make sure that whatever structure we end up coming up with is matching the degrees of unsaturation. So it's a good check. So let's go ahead and do that. So the formula for the degrees of unsaturation is 2 times the number of carbons plus 2 plus n, number of nitrogens, number of hydrogens, number of halogens, all over 2. And if you include all of the number of atoms of each type, you end up getting 4 degrees of unsaturation. So altogether, there is a sum of 4, altogether including the number of multiple bonds and rings, we get 4. Now we don't know how many rings there are, how many double bonds there are, but once we get our final structure, we can refer back to this value. So now let's look at the IR spectra. So right away, one of the easiest things that I like to look for is an OH band. And if we look at this, we see that there is definitely an OH band right here, because it's past 3000 and there's a broad curve, right? And that's what we're looking for when we're looking for an OH band. So that's one thing. The next thing is we're looking for, when we see the region right around 3000, this region tells us about our carbon-carbon and our carbon-hydrogen bonds. So past 3000, we see a peak right here, and this peak corresponds to CC double bonds. So that definitely is good because it matches our check that we saw from our degrees of unsaturation. It tells us that, yeah, there are some multiple bonds involved in that total sum of 4 degrees of unsaturation. Now, the next thing is right before 3000, we see a CH bond. We see a peak around 2984.97. So that is also indicative of the fact that there are CH bonds. Now, one last thing we need to pay note to is that right before we hit the fingerprint region, we have one more peak, and it's right here, right around 1600. And what this peak tells us is that there is definitely an aromatic system. This is a big giveaway because that means that there's definitely a benzene ring involved as per the title of an aromatic system, and it matches our degrees of unsaturation as well. So when we draw out our aromatics, we can already start off with a rudimentary structure. Right, and the interesting thing about it is that there are 3 double bonds and there is 1 ring. So this already means that the sum, there's 3, so 3 multiple bonds and 1 ring gives us 4. And this matches our degree of unsaturation. So what this tells us is that there are no more double bonds or rings involved. So we're going to have substituents around this ring and nothing else, no additional, and those substituents won't be having their own sort of double bonds or there won't be additional rings. So it does simplify things a bit. Now, let's look at the NMR spectra. So we see that for, let's start upfield. So right around here, next to the beginning. Right, let's start upfield and let's go downfield. So right around 1, we see sharp peaks for 3 protons, and around this region it corresponds to CH bonds, right? So CH bonds, and these are just saturated protons, right? There's no sort of other group that's attached to it, no aryl groups, nothing like that. It's just a normal methyl group. And the reason why I know it's methyl is because of the fact that there's 3 hydrogens, right? So this is the first piece of information we get. The next piece of information is a little bit more downfield. We notice there's 2, there's a set of peaks, and they correspond, actually, if you look at like some sort of graph or a table for these types of values, shift values for different groups for NMR, what you find out is that this is actually an aryl sort of compound. So there's some sort of aromatic system, and there's also a carbon attached to it which has 2 hydrogens, and I know that because the integration number here is for 2 hydrogens, right? So another piece of information. Now here's a little bit of a trickier one. There's a 1 right here, and it's a small little peak. You might be tempted to ignore it, but just as a check, if you count the number of hydrogens in this whole thing, there's from this integration, you see there's 3 plus 2 plus 1 plus 2 plus 2. And this gives us a total of 10 protons. And if we look back at the chemical formula, there's 10 protons. So that means that we really can't ignore this peak. And if you look at a chart telling you the values for these types of peaks, the corresponding groups for these types of peaks, you learn that this is actually a peak for a OH group that's attached to a aromatic system. And lastly, we have a set of protons very much downfield, and they're around this region, right, 6 to 7. And so this is a big giveaway. These are referring to aromatic protons because of all the immense deshielding that occurs to these protons because of the fact that they're directly connected or bonded to a aromatic system. Now, here's where the tricky part is. Trying to find out how the substitution of, so from the NMR spectra, we see that really there are 4 protons, right? 4 protons attached directly to this aromatic structure. That means there's 2 substituents. Now, we don't know what those substituents are yet, but we should be able to find out how they are positioned relative to each other, right? There's 3 positions, right? Ortho, meta, and para. Now, ortho is if they're just attached to carbons that are adjacent. Meta is when they're basically 2 carbon, they're not adjacent, they're separated by 1 carbon. And para is when they're basically on opposite ends of the ring. So the question then becomes, how are these 2 groups positioned relative to each other? And that also affects where the protons are as well. The 4 protons are positioned. Thankfully for us, we have the simplest case here, because actually, if you look at the peaks, you'll find that in a way it's somewhat of a mirror plane if you don't include the intensity of the peaks. And what this tells us is that if you look at the splitting pattern, right, there is a doublet here and a doublet here. And by the n+1 rule, that means that it had to interact with only just one. A proton, an aromatic proton, only interacted with just one other proton. In order for you to get a doublet by n+1, you would have to just have one other proton you're doing spin-spin coupling with. So it doesn't make sense for you to have 2 protons next to you. And so let's say, for example, if I had a proton right here, and if I had another proton here and another proton here, all 3 aromatic protons, and let's look at this proton right here. So if, for example, and I'm just gonna, let's try out each one of these. Right, I just put sub 1 and sub 2 for substituent 1 and substituent 2. So clearly, if we look at the splitting pattern for this particular proton, we know that it's going to be affected by it's going to do spin-spin coupling with two protons here, right? And that's going to result in additional splitting, right? It's not going to give you a doublet. And so therefore we know, if we look at this particular configuration, right, we see that the two substituents are one carbon apart from each other. So we know that the meta position, right, that's what it corresponds to, is not going to give us the splitting pattern that we see. Now, how about we look at ortho? So if I was to just right now, both of these substituents are right next to each other. Again, the same issue arises because for protons that are closed in by two other protons, right, one on the left and one on the right, you're not going to get a simpler doublet, right? So that leaves us with para as our only possible configuration. So ortho is out, and that leaves us with para as our only possible configuration, and let's see how that would fare if we apply the same analysis. Clearly, if we were looking at, say, this proton, the only other chemically equivalent other proton which is not chemically equivalent that it can do spin-spin coupling is this proton right here, and that would give us a doublet. The same result would happen if we looked at, if we looked at this proton or this proton or this proton. But we note that there are actually two pairs of chemically equivalent protons. We have I'm just going to label this as HA, HA, HB, HB. And the reason why the two at the top are considered chemically equivalent is because they're by symmetry right next to the first substituent at the top, and so they're in a similar chemical environment. And the same argument goes for the protons at the bottom, HB. So that would explain why we have two sets of peaks here. And so we know for a fact now that we are left with the para position as our form of substitution. Now the issue is actually determining what the substituents are. And thankfully, this is not too hard of a task because from our IR spectra, we found that one of those is the hydroxyl group, right? A hydroxyl that is directly connected to the structure. Now here's where things can get a little tricky. We see that there is also a CH2 aryl bond as shown here, and I've drawn it at the bottom of that ring. But the question is, where does this go? Where do the CH3 saturated bonds go? It can't form another bond with, there can't be a third substituent, right? So what does this tell us? It tells us that we would have to form, there's a possibility that we would have to form that CH3 right here. But we can't just blindly say that, right? We need to back it up. So let's look at the splitting patterns of this substituent. So if we look at this carbon, right, and that carbon corresponds to the set of protons here, so we find that, actually, apologize, I meant to say that the protons correspond to this point. We find that there is a quartet, right? There's a quartet splitting. So that means by the n+1 rule, there must have been 3 chemically equivalent protons involved in spin coupling, in spin-spin coupling. And it makes sense that we would include that CH3 bond here in this case, right? Because the adjacent carbon has 3 chemically equivalent protons. So it matches that description. But just to make sure, let's look at the splitting pattern of our CH3, our saturated CH bonds. And here we see that there is a triplet. So that means by the n+1 rule that there's 2 chemically equivalent protons in spin-spin coupling. So this also makes sense because now let's work the other way backwards. For this carbon, the adjacent carbon has 2 chemically equivalent protons. And so this description matches everything so far that we've described in the proton NMR and the IR spectra. So in fact, this turns out to be our final answer. And with that, we have completed the final exam. And now we will proceed to the next section, which is the multiple choice questions. Hello everyone, now we've started the second portion of our review, which is the multiple choice section. So let's start off with the first question that I got from the review. It's a simple nomenclature problem, but it does test concepts in stereochemistry, which I found to be interesting. So it's not just a simple nomenclature problem. You have to also consider the aspect of stereochemistry. So let's dive right in. For the compounds, we're given 4 different choices, and we're asked what is the compound that matches the name. So right away, one of the first things we can do is we can just look at the easy notation of this compound. We see that it's a pentene, the main chain is a pentene, and we see that across that pentene, that the double bond corresponding to that pentene chain, there's an E configuration, and E, to recap, is when the priority groups are opposite to each other. So let's look at the answer choices. We haven't considered the rest of the name at all, but let's just look at this double bond and see. Does it match the easy? Is it E or is it Z, basically? So choice A, we find that the leading group on the right is the chlorine, and the leading group on the left is the ethyl substituent. And we find that they're opposite to each other. So this definitely matches the E configuration in the name. So it's one candidate. And in the second option, the right side is flipped. So now we have these two up here, but this is the Z notation because they're on the same side of the double bond. So that means they're not opposed to each other. They're not on opposite sides is what I'm trying to say. So this does not match the name description, so B cancels out. If we look at C, we find the following. We see that there is the leading group on the left is the methyl group, and the leading group on the right is this branched halide. And we find that they're on opposite ends, so we'll consider this as an option as well. Now for option D, it's basically option C, but the substituents on the right side have flipped, so Now they're on this. Now they're not opposite to each other. So that means it gets the Z notation. So this would not be an option. So just look at this. We just with the first part of the name, we were already able to cancel out two choices. So stereochemistry really does help for nomenclature problems, especially when it comes to multiple choice problems. The next thing to consider is the fact of how the chain is numbered. So let's look at the substituents first. We find that the substituents are on carbons 1 and 2 of the pentene. So in choice A, if we started from the left end and worked our way, no, never mind. That's not what I meant to do. If we start from this carbon and go until the end of the chain, what we find is that it matches that 1,2 dichloride description. There's a chlorine on carbon 1 and there's a chlorine on carbon 2, so that checks off. And in addition, 2 pentene, so that means it's corresponding to the first carbon of the double bond that is within this pentene chain. And when we look at option A, that matches the description as well, because the first carbon of the double bond, if we go from right to left, is at position 2. So it seems as though option A is our answer. And option C would not be correct, because if we apply the numbering in the same way that we did, right, if we started from the chloro groups, right, 1, 2, it matches that. But here's where the problem is. The first carbon for that double bond starts at the third carbon, which is not what the name says. The name says that it should start at the second carbon. So it wouldn't match the description, and therefore option C would be incorrect. And that's how we would solve the first problem. For this question, we are given a set of carbocations, and we're asked which carbocation is the most stable. So this seems like a simple question, but it's always good to make sure that we have a strong understanding of the stability of carbocations, because it's not like you're going to be tested over tertiary, secondary, and primary carbocations all the time. In fact, there will be odd ones like vanillic carbocations or allylic carbocations. So it's always important to make sure that you always you're aware of the stability of other forms of carbocations as well. So for the first carbocation, we see that it is just simply a tertiary carbocation. For part B, it's interesting because actually this is an allylic carbocation. There is a positive charge here, but that positive charge for that carbon, the carbon that's positively charged, is attached to a carbon that's double bonded. So this means that it's allylic, so it's possible to have a resonance structure, another resonance structure as well. And let's look at how the carbocation is in both scenarios. In this case, it's tertiary carbocation, but it's allylic as well, so that there's that additional resonance stabilization. In this case, it's a secondary carbocation, but it's also allylic. So let's keep that in mind. Option C, we have an allylic again, because there's a positively charged carbon that's bonded to a carbon that's doubly bonded to another carbon. So let's see, it's secondary carbocation and it is allylic. So let's draw out the resonance structure. And we see that this resonance structure is also secondary and allylic. And lastly, we have vinylic carbocation, because the carbocation is directly on top of a carbon that's double bonded. Now looking at these four choices, right away I can see that vinylic carbocation is very, very, very unstable, and so therefore you can immediately cancel that out as a choice. For A, it is a tertiary carbocation, but it doesn't have any resonance whatsoever. So there is compared to options B and C, it's not as effective in terms of stability. So we can cancel this out as well. Now we're down to B and C. And in B, one of the resonance structures is actually a tertiary carbocation and allylic. While in option C, both of them are secondary carbocations. So the second option does have an advantage in the fact that it has one resonance structure at least that has a tertiary carbocation. So that means that B would actually be the most stable structure out of all four of these. For this question, we are given 4 different compounds and we're asked to rank them based on the order of decreasing acidic strength. So I know that when we think of acid strength, the first thing that comes to mind is the stability of the conjugate base. So just to save time, I have written out all of the conjugate bases for these compounds. And when we look at these conjugate bases, it's not so easy to tell, well, which one is more stable because we're not dealing with resonance or any of the typical indicators of stability. So here we have to take a step back from our traditional approach and just look at the acids themselves first. So we see that in this case, there's a positive charge for the first 2 compounds on the oxygen atom, but there is a positive charge on the nitrogen atom for the second 2. Now, if we look at the periodic table, we see that oxygen is a more electronegative atom than nitrogen, so it's less capable of holding positive charge in a stable manner. And because it is less stable, it actually means that it's more reactive or a stronger acid. And this means that 3 and 4 cannot be the most acidic species. So right away, without even looking at the conjugate bases, we can automatically cancel out D and C as our answers because we know that 3 and 4 can't be the strongest acids, because they're more stable than the first 2, because nitrogen can hold positive charge better than an oxygen atom. Now let's look at options A and B. Well, there's 2 ways we can go about this. We can either compare 1 and 2, or we can compare 3 and 4. And either way, it will get us to the same result. So if we look at 3 and 4, we see that everything is the same except there is 2 methyl groups here, and then there's 3 trichloro groups here. And what this means, what this is referring to, is the inductive effect. What this is trying to test you on is the inductive effect on acidity. So we know that if there's very strong inductive groups like this on a compound as compared to a structure that doesn't have inductive groups like this one, we know that it takes away electron density from the places where the protons are. So this actually makes it more acidic makes 4 more acidic than 3. So automatically this ends up allowing us to choose A as our final answer. But let's also look at 1 and 2 just to be thorough. So if we look at 1 and 2, we see that the oxygen atom, right? The oxygen atom on this first compound is sp2 hybridized. Now, if we look at the next one, we see that it is sp3 hybridized. So, what do we know about sp2 and sp3? Well, sp2 has 1/3 S character and 2/3 p character, referring to the s and p orbitals. And the more S character your hybridization is, the more basic it is. That's the principle, right? So if more of that hybridized orbital consists of the s orbital, that means that the electron pair, so the electron pair right here, it becomes more stable. So that allows it to be less basic. And what this tells us is that sp3, right? sp3 even has a lower S character. It has 25% S character. And so if we look at this, we see right away that if you have more S character, right? If for part 1, it has 1/3 S character. So that means that its electrons are more stable and thus less basic and thus more acidic. So that also allows us to get A as our final answer. I apologize, I know it was a more of a convoluted way, but there's 2 ways to getting to this solution. And it's easier if we just consider options 3 and 4 with the inductive effect, but just to be thorough, I presented the other comparison as well. For this question, we are given a reaction and we're asked to assign to determine the stereochemical classification of this product, the major product. So when we look at this reaction, we see that it is an alkene reacting with hydrobromic acid. And right away, this should ring in your head that this is an electrophilic addition reaction because there's a double bond and you're adding an acid, namely HBr, hydrohalic acid, namely HBr, to that, and it will result in a electrophilic addition reaction. So by Markovnikov's rule, right, we need to add the hydrogen to the side that has the side of the double bond that has more hydrogens, and in this case that would be the left side because that carbon is attached to 1 hydrogen, while on the right side this carbon is only attached to 2 methyl groups. So it's going to be on the left side. So, and the bromine, on the other hand, will be on the right side. And if we take that into consideration, right, applying Markovnikov's rule, we get the following product. Now when we look at this product, we see that there are no chiral carbons or stereocenters whatsoever. All of these have groups that have several, like basically there are 4 carbons, but each of these carbons are attached to, are not attached to 4 unique groups. and none of them are attached to 4 unique groups. So right away that tells us that there are no stereocenters in this molecule, and therefore there is no chirality. So that means that this is simply achiral, or C, as the final answer. For the next question, we are given the following products, and we are asked to determine the structure of the reactant that would allow us to get these two products. And the reagent that we have is methanol. So the question is, how do we work backwards to get to that point? So let's look at the functional groups on our products. We see that both of them have ethers. Both of them have a phenol substituent. But the thing that separates them is that one has an alkene. I need to denote that with a different color. And one has a methoxide group. And when I think of the methoxide, and I remember that one of our reagents, that our reagent is methanol, I'm very much suspecting that we have a substitution reaction. And since when I see this double bond that is in this second group, I am suspecting an elimination. So in order to have a combination like this, you need to have a SN1 and a SN1E1 reaction combo. And the reason why is because this type of competition isn't as observed for SN2 and E2. And you're involving a reagent which is not a super strong base as you would expect for something like an E2 reaction. So basically, let me note it down, dealing with SN1 and E1. So if we work backwards, right, we know that we can get to this point, retrosynthetically speaking, from an alkyl halide. SN1 reaction. If we had a carbocation at this point, right, if we worked backwards. Now, among all the other choices present, option A, how do we get from this to this? How would we do that? There would be no way for us to get from there to there without inducing some form of removing a proton. And how would we get from here So what I had meant to say earlier was, so since this is SN1 and E1, they originate from one place, which is this, right, from the carbocation. And because that's the case, then we would have to basically find out which of the choices would allow us to get to this carbocation. And the simplest path really is C. C is the one that allows us to get to this carbocation. In order for us to form that carbocation, all this bromine has to do is to leave, and it forms a stable tertiary carbocation. So C is the answer for this problem. Apologize for the earlier confusion, but this is how we would get to our solution. So this is simply just applying retrosynthesis, but for a multiple choice problem. For the problem here, we see that we are given a cycloalkene with a substituent, and it undergoes a sequence of steps. But if we look at this reaction sequence and we want to find out what the product of this reaction is, if we look at it carefully, very much resembles B2H6, which is diborane. And diborane can also be represented by BH3THF, which is the common reagent in hydroboration oxidation reaction. The only twist here is that instead of working with hydrogen, we're actually working with its cousin, or its isotope, deuterium. So the thing about hydroboration oxidation reactions is that it's an addition reaction that is going to add that will follow anti-Markovnikov addition, and it will also be syn addition, so it will be on the same side of the cyclic molecule. And in this case, since we're working with a deuterium-based version of diborane, that means that we want to add deuterium and a OH across this double bond. Now the question is, okay, so if we're going to do that and it has to be syn addition, that automatically rules out options D and C, because in this case the deuterium and the OH groups are on the opposite side of the cyclic plane, right? Not on the same side. It's not syn addition. So those two options are out. But now we look at A and B. And A and B are interesting because now we get to consider regioselectivity. So this is where anti-Markovnikov addition comes in, right? This problem is nice because it's testing us on all the aspects of hydroboration oxidation. So since it's anti-Markovnikov, we're going to add that deuterium to the carbon that has the least number of hydrogens instead of the carbon that has the most number of hydrogens. So that means that we would end up with having A as our final answer because the deuterium is placed on the carbon, which only had a CH3 before it had no proton. So this is anti-Markovnikov addition. This would be Markovnikov. But that is not this is not what the hydroboration oxidation reaction does. It does anti-Markovnikov. So please keep that in mind. This problem is interesting because now we are studying carbon-carbon. Now we're doing multiple choice questions on reactions that form carbon-carbon bonds. And we see that the question asks which combination of reagents would not result in the alcohol shown in the box to the right, top right. So let's look at each one of these options. For option A, we see that you can react this aldehyde with a Grignard reagent containing a methyl group. And if you do that, you end up forming the following product, because now you're adding this CH3 group to that carbonyl carbon, and I apologize, I meant to say even though you formed this negatively charged oxygen, this is for the first step, by the way, just the first step. Now we have to do a reductive workup with water, and that causes it to become an OH. Applying the same logic, we would end up with a product like this, because now we have an ethyl group, right? So to the right of this carbonyl carbon, I will write out an ethyl group. And if you compare these two final structures to the one in the box, you see that they're basically the same. So these two reactions would produce the alcohol, and that's not what we want, so A and C are out. Option B, we are reacting this ketone with sodium borohydride, followed by a reductive workup, and this reaction will actually convert the ketone into a secondary alcohol. And it turns out that this secondary alcohol is the, made a mistake. I should have included a CH here. A CH here. So that allows us to get to the same final answer, so B would not be a choice either. And now that leaves us with D as our final answer. Because when we react this with a Grignard reagent, we end up actually forming a tertiary alcohol. Tert-butanol. And this is not matching the alcohol shown at the top right. So this would be our final answer for that problem. And now we reach our very last question of the review session. And in this problem, we're given this reaction with this ester, and it reacts with the lithium aluminum hydride in ether, and then followed by water. So right away, when you see lithium aluminum hydride, you should be thinking that this is there's going to be some strong reduction ahead of you, because lithium aluminum hydride is one of the strongest, if not the strongest, reducing agents that you're going to encounter in this class. And it's capable of reducing basically any form of oxidized compound, functional group, down to an alcohol. And that means that in this process, you don't stop it at merely an aldehyde, or you don't convert it to some sort of, you don't convert this into a ester. You end up converting it to an alcohol. It's not possible for these reactions involving lithium aluminum hydride to go all the way down to a alkyl group, which is in this case the methyl group. So that would not be possible either. So when you think of a lithium aluminum hydride, it's a safe assumption to make that, not assumption, it's known that this reagent is very capable of reducing esters, carboxylic acids, all the way down to to an alcohol. So that is why we would have A as our final answer. And with that, we have concluded this review session. Thank you so much for attending. I know it's been long, but I wish you the best of luck in your final exam. And please make sure to practice as much as possible, because that's what really helps you out in this class, as you already know. So with that, I wish you best of luck. Thank you.